Have you ever wondered what's really going on inside an aircraft engine? Four strokes, two revolutions, one single controlled explosion. This is the mechanical heart of flight. So let's go ahead and dive into what is truly a masterclass of mechanical engineering. All right, before we dive deep inside a single cylinder, we really need to zoom out and look at the whole engine. You see, the shape an engine takes, it's never an accident. It's a direct response to what the aircraft needs to do. It's a perfect example of form following function. So you had the early inline engines, right? They were all about that narrow aerodynamic profile. But then World War II comes along with its insane power demands, and suddenly the V engine is king. You also had these incredible radial engines, just amazing power-to-weight ratios, and that huge frontal area, perfect for air cooling. Fast forward to today, and you'll find that most light aircraft, your Cessnas and Pipers, they use a flat or horizontally opposed engine. Why? Because it's compact, it's streamlined, and it's just a naturally strong, rigid design. Okay, so we've seen the different shapes. Now let's strip away all that external metal and complexity. We're going to look at the perfect theoretical rhythm that beats inside every single one of those cylinders. We're talking about the Otto cycle in its purest, most ideal form. So what is the Otto cycle? Well, at its core, it's the fundamental four-stroke process that turns chemical energy, fuel, into motion. And a stroke? That's just the piston traveling from its highest point, what we call top dead center, or TDC, all the way down to its lowest point, bottom dead center, or BDC. You get two strokes down, two strokes up, and that completes the cycle. Think about that for a second. The crankshaft has to make two full turns, that's 720 degrees of rotation, just for one single power event. So in a perfect, theoretical world, it's a beautiful, simple dance. First up, you've got the induction stroke. The piston drops, and that sucks the fuel and air mixture right into the cylinder. Then comes the compression stroke. The piston travels back up, squeezing that mixture tight. Third, the big one, the power stroke. A spark ignites the mixture, and that expansion forces the piston down with incredible power. And finally, the exhaust stroke. The piston comes up one last time, pushing all those burnt gases out to make way for the next cycle. But wait, there's actually a crucial fifth event, kind of tucked in between compression and power, and that's combustion. Now, this is absolutely critical to understand. This is not an explosion. It's a very rapid, but very controlled burn, and it happens at a constant volume, right when the piston pauses for just a split second at the very top. This controlled release of energy, well, that's the whole ballgame. It's the entire source of the engine's power.
You know, that theoretical cycle is elegant, it's clean, but it's just not very efficient in the real world. So now we have to move from the clean world of physics theory into the messy, brilliant world of engineering, where smart compromises have to be made to deal with reality. So here's the puzzle engineers had to solve. The fuel and air mixture. It's a fluid, right? And like any fluid, it has mass and it has inertia. It doesn't want to start moving, and once it gets going, it doesn't want to stop. You can't just snap the valves open and closed instantly at the top and bottom of the stroke. It just doesn't work that way. So, what do? The solution is absolutely brilliant. You optimize the valve timing. Instead of opening the intake valve right at the top, you give it a valve lead. You open it a little before the piston gets there to get the flow started. Then you use valve lag, keeping it open just a little bit longer as the piston starts to come back up. You're using the mixture's own momentum to cram just a little more into the cylinder. Now, this creates a fascinating moment called valve overlap, where for a split second, both valves are open. And here's the genius part. The momentum of the exhaust gas rushing out actually helps pull the fresh fuel and air mixture in. It's called scavenging, and it dramatically improves the engine's efficiency. Now, during that compression stroke, something really cool from physics happens. It's called adiabatic heating. If you've ever used a bicycle pump and felt it get hot, you've experienced this. By simply compressing the gas, the fuel-air mixture, you raise its temperature, even without adding any external heat. This isn't a small thing either. It contributes a lot to the pressure rise in the cylinder, basically priming the mixture for a much more powerful and efficient burn. So as a pilot, you can't see any of this incredible physics happening inside the cylinder, right? But you do see its direct effect on one key instrument, the manifold absolute pressure gauge, or the MAP gauge. When you move the throttle, what you're really doing is controlling a valve that regulates the pressure in the intake manifold. That pressure dictates how much of a breath the engine can take, and that, in turn, dictates how much power it makes. Okay, so we've got this amazingly complex dance happening thousands of times every minute. So how do we actually measure it? How do we talk about its performance, its efficiency, and its power?
When we talk about power, we usually talk about horsepower, but it's not that simple. There are actually three types you need to know. First, there's indicated horsepower. That's the total theoretical power being made inside the cylinder from combustion. But you lose some of that power just to internal friction, all those moving parts rubbing against each other. That's friction horsepower. So what you're left with, the actual usable power that gets to the propeller, is called brake horsepower. The formula is simple. Indicated horsepower minus friction horsepower equals brake horsepower. And that is the number that actually matters for flight.
Now, when we get to efficiency, well, the numbers can be a little sobering. Mechanical efficiency, how well the power gets from the piston to the prop, is actually pretty good, about 85%. And volumetric efficiency, how well the cylinder fills up with air and fuel, that's also around 85%, thanks to that clever valve timing we talked about. But here's the real shocker: thermal efficiency. Of all the potential heat energy locked inside the fuel, only about 28% actually gets turned into useful work. Where does the rest go? It's just lost as waste heat. It's an unavoidable price you pay for turning heat into motion.
So, how do engineers measure fuel efficiency with real precision? They use a metric called specific fuel consumption, or SFC. All it is the weight of fuel, usually in pounds, that an engine needs to burn to make 1 horsepower for 1 hour. For engine designers and pilots, getting the lowest possible SFC is the holy grail. It means you're wringing out more power from every single drop of fuel. And one of the most critical design choices that affects all of this is the compression ratio. It's simple, really. It's the ratio of the total volume in the cylinder when the piston is at the very bottom, compared to the tiny volume left when the piston is at the very top. The rule of thumb is, the more you can squeeze that fuel-air mixture before you ignite it, the bigger the bang you get and the more power and thermal efficiency you can extract. All right, we've looked at the theory, we've looked at the real-world compromises, and we've seen how we measure performance. Now for the fun part. Let's actually build this engine piece by piece and see how this incredible mechanical symphony all comes together. Everything, and I mean everything, starts with the crankcase. You can think of it as the foundation or the backbone of the entire engine. Its job is to be unbelievably strong and rigid because it has to hold all of these incredibly fast-moving parts in perfect, precise alignment, all while dealing with immense forces. And bolted inside that crankcase is the crankshaft. Honestly, this component has one of the toughest jobs in the whole machine. It has to take that violent, linear, up and down slamming force from the pistons and somehow, flawlessly, convert it into the smooth, powerful rotation that spins the propeller. This is literally the part that turns controlled fire into flight. That incredible force from combustion gets captured by the piston. It's basically a moving, gas-tight plug that slides up and down inside the cylinder. To do its job, it has compression rings on top to seal in that immense pressure, and it has oil control rings on the bottom to manage lubrication. And all of that force is then transmitted down to the crankshaft through the super strong connecting rod. Now, all of this magic happens inside the cylinder assembly. You've got the cylinder barrel, which is the super hard, perfectly smooth track that the piston runs in. Bolted on top is the cylinder head. It seals everything up, and it's where you'll find the spark plug and the engine's lungs, the intake and exhaust valves. And those valves, they're held shut by incredibly powerful springs to make sure they don't bounce or float when the engine is running at high speed. So what controls these valves with such perfect millisecond timing? That would be the camshaft. And here's a really neat detail. It's geared to spin at exactly half the speed of the crankshaft. Now, why would that be? Well, think about it. Each valve only needs to open once for every 2 turns of the crank in a 4-stroke cycle. The carefully engineered shape of the lobes on the shaft, that is the physical, mechanical embodiment of the practical Otto cycle. It's what dictates the precise timing of valve lead, lag, and that all-important overlap. So when you step back and look at it, we go from a simple 4-stroke theory to this incredibly complex symphony of precisely timed mechanics. The piston engine is just an absolute marvel of engineering ingenuity. It's what has powered us through the skies for more than 100 years. But, as technology keeps marching forward, it does leave us with a question. What will be the mechanical heart of the next generation of flight?